Look up at the night sky. Those pinpoints of light you see represent just a tiny fraction of what's actually out there. And here's the thing that should absolutely blow your mind. Despite thousands of years of human civilization, centuries of scientific inquiry, and decades of space exploration with the most advanced technology ever created, we still don't understand what most of the universe is made of. We don't know why it exists the way it does. We don't even know if we're alone in it. Welcome to the greatest detective story ever told. One where the clues span billions of light years and the suspects include invisible matter, phantom energy, and perhaps civilizations we've never encountered. This is a journey through the cosmic mysteries that keep astronomers, physicists, and cosmologists awake at night. The puzzles that remind us how much we still have to learn about the reality we inhabit. When we talk about cosmic mysteries, we're not discussing minor gaps in our knowledge or technical details waiting to be filled in. We're talking about fundamental questions that strike at the heart of existence itself. These are the problems that, when solved, will completely revolutionize our understanding of reality. They're the kinds of mysteries that make scientists question whether our most successful theories are actually wrong, or at least seriously incomplete. Think about this for a moment. We've mapped the human genome. We've detected gravitational waves rippling through space-time. We've landed rovers on Mars and sent probes beyond our solar system. We've built particle accelerators that recreate conditions from fractions of a second after the Big Bang. And yet, we can only account for about 5% of the universe. 5%. The other 95% is something we call dark matter and dark energy, and we genuinely don't know what either of them actually is. Imagine being a detective who can only see 5% of the crime scene. That's where we are right now in cosmology. But here's what makes these mysteries so compelling. They're not abstract philosophical questions. They have real, observable consequences. Dark matter holds galaxies together. Dark energy is literally tearing the universe apart, causing space itself to expand at an accelerating rate. These aren't theoretical constructs. They're forces and substances that shape the very fabric of reality. And we're stumbling around trying to understand them with the intellectual equivalent of a flashlight in a cosmic warehouse. The beautiful thing about science, though, is that admitting ignorance isn't a weakness. It's the starting point for discovery. Every major breakthrough in human history began with someone saying, "We don't understand this, and we need to figure it out." Newton didn't understand why objects fell to Earth, so he developed the theory of gravity. Einstein didn't understand why the speed of light seemed constant regardless of the observer's motion, so he revolutionized our understanding of space and time itself. The mysteries we're going to explore in this video are our generation's great unknowns. And somewhere out there, perhaps watching this right now, might be the person who finally cracks one of them. These cosmic puzzles also matter because they connect to profound questions humanity has asked since we first looked up at the stars. Are we alone? What is the universe made of? How did it begin, and how will it end? What are the fundamental laws that govern everything? These aren't just scientific questions. They touch on philosophy, religion, and our sense of place in the cosmos. When we solve these mysteries, we're not just adding to a database of facts. We're fundamentally altering humanity's understanding of its relationship to the universe. Consider the Fermi Paradox. The question of why we haven't detected any signs of alien civilizations despite the seemingly high probability that they should exist. This isn't just about whether little green men are out there. It's about understanding whether intelligence is common or rare, whether technological civilizations tend to destroy themselves, whether we're looking in the wrong places or in the wrong ways, or whether we're genuinely alone in a universe vast beyond comprehension. The answer to this mystery will reshape how we think about our own future and our cosmic significance. Or take the mysteries surrounding black holes, objects so extreme that they break our understanding of physics. At the event horizon of a black hole, quantum mechanics and general relativity, our two most successful scientific theories, come into direct conflict. They make predictions that contradict each other. One of them must be wrong or incomplete, or they need to be unified in a way we haven't figured out yet. Solving the black hole information paradox isn't just about understanding these cosmic monsters. It's about discovering a more fundamental theory of reality itself. What's particularly exciting about this moment in history is that we have better tools than ever before to tackle these mysteries. The James Webb Space Telescope is peering deeper into space and further back in time than ever before. Gravitational wave detectors are opening an entirely new way of observing the universe. Particle accelerators and dark matter detectors are becoming more sensitive. Artificial intelligence is helping us process astronomical data at scales that would have been impossible just years ago. We're living in a golden age of cosmic discovery, where questions that seem permanently unanswerable are suddenly within reach. But we also need to be humble. History is littered with examples of scientists who thought they were on the verge of a complete understanding of nature, only to have their worldview completely overturned by the next generation's discoveries. In the late 19th century, some physicists believed that all the major questions had been answered and only minor details remained. Then came quantum mechanics and relativity, and everything changed. The mysteries we're exploring today might be solved in ways we can't even imagine yet, using frameworks and concepts that haven't been invented. That's what makes this journey so thrilling. We're not just cataloging what we don't know, we're standing at the frontier of human knowledge, looking out into the unknown. Every mystery we'll discuss represents an opportunity for a breakthrough that could be as revolutionary as the discovery that Earth orbits the Sun, or that time and space are interconnected, or that the universe had a beginning. Dark matter, the invisible scaffold of the universe. Imagine discovering that everything you can see, every star, every planet, every galaxy, every nebula, everything that emits light or can be directly observed, makes up less than 1/6 of all the matter in the universe. The rest? It's invisible. It doesn't emit light. It doesn't absorb light. It doesn't reflect light. It's completely transparent to the entire electromagnetic spectrum. And yet, without this invisible substance, galaxies would fly apart, galaxy clusters would dissolve, and the large-scale structure of the universe, as we know it, simply wouldn't exist. Welcome to the mystery of dark matter, perhaps the most humbling puzzle in modern physics. The story of dark matter begins not with what we can see, but with what we can measure. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a collection of over 1,000 galaxies bound together by gravity. He did something quite straightforward. He measured how fast these galaxies were moving. What he found didn't make sense. The galaxies were moving so fast that, according to the visible mass in the cluster, they should have escaped the cluster's gravitational pull long ago. It would be like spinning a ball on a string so fast that the string should break, except the string somehow holds anyway. Zwicky proposed that there must be some invisible matter, some dunkle materie, or dark matter, providing additional gravity to hold everything together. For decades, Zwicky's observations were largely ignored or dismissed. Then, in the 1970s, astronomer Vera Rubin made observations that would change everything. She was studying the rotation curves of spiral galaxies, measuring how fast stars orbit around the galactic center at different distances. According to Newton's laws and everything we understood about gravity, stars farther from the center should orbit more slowly, just like how Neptune orbits the Sun more slowly than Earth does. But that's not what Rubin found. Stars at the outer edges of galaxies were moving just as fast as those closer to the center, sometimes even faster. The only explanation was that there must be a massive halo of invisible matter surrounding these galaxies, providing the extra gravitational pull needed to keep those outer stars moving at such high speeds. Since then, evidence for dark matter has piled up from multiple independent sources. And this is crucial because in science, when completely different types of observations all point to the same conclusion, you're probably onto something real. Gravitational lensing, the bending of light by massive objects predicted by Einstein's general relativity, shows us that there's far more mass in galaxy clusters than we can account for with visible matter. The cosmic microwave background radiation, the afterglow of the Big Bang, contains subtle patterns that only make sense if dark matter exists and makes up about 27% of the universe's total energy content. Computer simulations of how the universe evolved from the Big Bang to today only match what we actually observe when we include dark matter in the calculations. So we know dark matter exists, or at least we know that something is producing gravitational effects that we can't explain with ordinary matter alone. But here's the mystery that keeps physicists up at night. We have absolutely no idea what it actually is. Let's talk about what dark matter isn't. It's not just ordinary matter that happens to be dark, like planets or black holes or clouds of gas that don't emit light. We call regular matter baryonic matter because it's made of particles like protons and neutrons, which are types of baryons. We can actually calculate how much baryonic matter should exist in the universe based on Big Bang nucleosynthesis, the process that created the first atomic nuclei in the early universe. The math is extremely precise, and it tells us there simply isn't enough ordinary matter in the universe to account for the gravitational effects we observe. Dark matter has to be something else entirely, something non-baryonic. The leading candidate has been WIMPs, weakly interacting massive particles. These hypothetical particles would barely interact with ordinary matter except through gravity and possibly the weak nuclear force. Imagine billions of dark matter particles streaming through your body right now, passing through you like you're not even there, because they simply don't interact with the electromagnetic force that governs how normal atoms and molecules behave. WIMPs are attractive theoretically because they emerge naturally from extensions of the standard model of particle physics, particularly from theories like supersymmetry that attempt to solve other problems in physics. But here's the frustrating part. Despite decades of increasingly sensitive experiments, we haven't detected a single WIMP. Deep underground laboratories around the world house detectors cooled to near absolute zero, shielded from cosmic rays and other interference, waiting for the telltale signal of a dark matter particle colliding with an atomic nucleus. Experiments like Xenon, LUX, and Panda-X have pushed the sensitivity to extraordinary levels, and they've found nothing. The parameter space where WIMPs could be hiding is shrinking year by year. This has led physicists to explore alternative candidates. Axions are ultralight particles originally proposed to solve a different problem in particle physics, but which could potentially make up dark matter if they exist in sufficient quantities. Sterile neutrinos, hypothetical cousins of the known neutrinos, are another possibility. Some physicists have proposed primordial black holes, not the kind formed from collapsing stars, but tiny black holes that might have formed in the extreme conditions of the early universe. Each of these candidates has its own dedicated detection experiments and observational programs. Then there's an even more radical possibility. Maybe dark matter doesn't exist at all, and we need to modify our understanding of gravity itself. Theories like MOND, modified Newtonian dynamics, propose that gravity behaves differently on very large scales than we currently think. While MOND can explain some galaxy rotation curves quite well, it struggles to account for other observations like gravitational lensing and the cosmic microwave background patterns. Most physicists view modified gravity theories as less likely than particle dark matter, but they remain on the table because, honestly, we're still groping in the dark. If dark matter is humbling, dark energy is downright terrifying. Not because it poses any immediate danger to us, but because it represents something so fundamentally weird, so completely unexpected, that it has forced physicists to question whether we understand anything about the universe at all. Dark energy is the name we've given to whatever is causing the expansion of the universe to accelerate, to speed up over time. And here's the kicker. It makes up roughly 68% of everything in the universe. The majority of reality is something we discovered barely 25 years ago and still can't explain. Let's start with what we thought we knew. In 1929, Edwin Hubble made one of the most important discoveries in the history of astronomy. By studying distant galaxies, he found that they were all moving away from us, and the farther away they were, the faster they were receding. The universe, it turned out, was expanding. This was revolutionary because it meant the universe had a history. It hadn't always existed in its current state. If you run the expansion backward in time, you get to a point roughly 13.8 billion years ago when everything was compressed into an infinitesimally small, incredibly hot, dense state, the Big Bang. Now, if you have an expanding universe filled with matter and energy, what would you expect gravity to do? It should slow down the expansion, right? Gravity is an attractive force. It pulls things together. So physicists assumed that the expansion of the universe was gradually decelerating. The big question was whether there was enough matter in the universe for gravity to eventually halt the expansion and cause everything to collapse back in a big crunch, or whether the universe would expand forever, just at an ever-slowing rate. Those were the options on the table. Everyone was trying to measure exactly how much the expansion was slowing down. In the late 1990s, two independent teams of astronomers set out to measure this deceleration with unprecedented precision. They used type I supernovae as cosmic distance markers. These stellar explosions are incredibly useful because they all have roughly the same intrinsic brightness, which means if you measure how bright they appear from Earth, you can calculate how far away they are. By comparing the distances to these supernovae with their redshift, which tells you how fast they're moving away, you can map out the expansion history of the universe. Both teams, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, expected to measure how much the expansion was slowing down. What they found instead shocked the scientific world. The expansion wasn't slowing down at all. It was speeding up. Galaxies weren't just moving away from each other. They were moving away faster and faster as time went on. It was as if you threw a ball into the air, and instead of slowing down as it rose, it started accelerating upward. This was so unexpected, so contrary to everything we thought we understood, that the team spent months checking and rechecking their data, convinced they must have made a mistake somewhere. But there was no mistake. The universe's expansion is accelerating, and this discovery earned the 2011 Nobel Prize in Physics. The problem was nobody knew why. There was no known force or substance that could cause this. So physicists did what they often do when confronted with something inexplicable. They gave a name. They called it dark energy, not because we understand what it is, but because we need to call it something. What could dark energy be? The most straightforward explanation, and the one that currently fits the data best, is the cosmological constant. This is actually an idea that goes back to Einstein. When he first applied his general relativity equations to the universe as a whole, he found that they predicted an expanding or contracting universe, not the static universe everyone believed in at the time. So Einstein added a term to his equations, the cosmological constant, essentially a form of energy inherent to space itself that could counteract gravity and keep the universe static. When Hubble later discovered the universe was actually expanding, Einstein reportedly called the cosmological constant his biggest blunder and removed it from his equations. But it turns out Einstein's blunder might actually be correct, just not in the way he intended. If empty space itself possesses energy, what we call vacuum energy, then this energy has a peculiar property. As the universe expands and creates more space, it creates more dark energy. Unlike matter, which gets more dilute as space expands, the density of dark energy remains constant. This means that in the early universe, when everything was compressed together, matter and radiation dominated. But as the universe expanded, dark energy became proportionally more important, eventually becoming the dominant component and causing the expansion to accelerate. Here's where things get really strange. When physicists try to calculate how much vacuum energy there should be based on quantum field theory, they get an answer that's wrong by a factor of 10 to the power of 120. That's not a typo. That's 1 followed by 120 zeros. It's arguably the worst prediction in the history of physics. Either our quantum theories are catastrophically wrong about vacuum energy, or there's some unknown mechanism that almost perfectly cancels out this enormous value, leaving behind just the tiny amount we observe. Neither option is satisfying. Some physicists have proposed alternatives to the cosmological constant. One idea is quintessence, a dynamic form of dark energy that changes over time, unlike the constant vacuum energy. Others have suggested modifications to general relativity itself at cosmic scales, though these face challenges similar to modified gravity theories for dark matter. There are even more exotic proposals involving extra dimensions or interactions with fields we haven't discovered yet. What makes dark energy particularly unsettling is what it means for the future of the universe. If dark energy continues to dominate, and current evidence suggests it will, then the universe's expansion will keep accelerating forever. Galaxies outside our local group will eventually recede so fast that their light will never reach us. Billions of years from now, astronomers in the Milky Way would look out and see an apparently empty universe, with no evidence that other galaxies even exist. The universe will become colder, more dilute, heading toward what's called heat death, a state of maximum entropy where no useful energy remains to power stars, planets, or life. On a summer day in 1950, physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. The conversation turned to recent reports of UFO sightings, and the discussion wandered into the possibility of faster-than-light travel and alien civilizations. Then Fermi asked a question so simple, yet so profound, that has haunted scientists ever since. Where is everybody? It seems like such a straightforward question, but it encapsulates one of the deepest mysteries we face. The universe is vast, almost beyond comprehension. Our galaxy alone contains somewhere between 100 and 400 billion stars, and there are at least 2 trillion galaxies in the observable universe. That's more stars than grains of sand on all the beaches on Earth, multiplied many times over. We now know that planets are common. Most stars have them. We've discovered thousands of exoplanets, and many orbit in the habitable zone where liquid water could exist on their surface. The building blocks of life, complex organic molecules, are found throughout interstellar space. The universe appears to be teeming with the raw ingredients for life. So where is everybody? Why haven't we detected any signals from alien civilizations? Why hasn't anyone visited us? Why does the universe seem so conspicuously silent and empty when, by all reasonable calculations, it should be buzzing with activity? Let's put some numbers to this to understand why the paradox is so troubling. Our sun is a fairly typical star, and it's relatively young at about 4.5 billion years old. There are stars in our galaxy that are billions of years older. If even a tiny fraction of those older star systems developed intelligent life, they would have had an enormous head start on us, potentially millions or even billions of years. Now, humanity went from the first radio transmission to landing on the moon in less than 70 years. From the Wright brothers to the International Space Station in just over a century. Imagine what a civilization could accomplish with a million-year head start, or 10 million, or 100 million, even without faster-than-light travel, which may be impossible according to our current understanding of physics. A sufficiently advanced civilization could colonize the entire galaxy using conventional spacecraft traveling at a fraction of the speed of light. Calculations suggest it would take somewhere between 5 and 50 million years to spread across the Milky Way this way. That sounds like a long time to us, but it's actually a blink of an eye in cosmic terms. Our galaxy is over 13 billion years old. There has been plenty of time for civilizations to arise, develop technology, and spread throughout the galaxy many times over. And yet we see nothing. No megastructures harvesting the energy of stars. No signs of stellar engineering or galaxy-spanning infrastructure. No radio signals that clearly indicate intelligent origin, despite decades of SETI, the search for extraterrestrial intelligence, scanning the skies. The cosmic silence is deafening. This is the Fermi Paradox, and it demands an explanation. Over the decades, scientists have proposed hundreds of potential solutions, and examining them reveals just how profound and unsettling this mystery really is. One category of solutions suggests that life, or at least intelligent technological life, is incredibly rare. Maybe the emergence of life requires such a specific and unlikely set of circumstances that Earth is one of the only places where it happened. This is sometimes called the rare Earth hypothesis. Perhaps you need a planet exactly the right size, at exactly the right distance from a star of exactly the right type, with a large moon to stabilize its rotation, with a Jupiter-sized planet in the outer system to deflect asteroids, with plate tectonics to regulate the atmosphere, and on and on. Stack enough requirements together, and maybe we really are alone, or at least so rare that the nearest civilization is billions of light years away. But many scientists find this unsatisfying. Yes, Earth is special, but the universe is so incomprehensibly large that even incredibly improbable events should happen countless times. If the odds of life emerging on any given planet are 1 in a trillion, there should still be hundreds of billions of planets with life in the observable universe. Maybe life is common, but intelligence is rare. Perhaps the jump from simple organisms to complex multicellular life is extraordinarily difficult. On Earth, it took roughly 3 billion years to go from the first life to complex animals, whereas it only took a few hundred million years to go from the Cambrian explosion to humans. Maybe that first transition is the real bottleneck, and most life-bearing planets are stuck with nothing more complex than bacteria. Or maybe intelligence is common, but technological civilization is rare. After all, Earth has had billions of species over its history, and only one has developed technology capable of radio communication and space flight. Perhaps that's genuinely unusual. Maybe most intelligent species don't develop technology, or don't develop the specific kind of technology that would make them detectable or expansionist. Then there are the darker explanations, collectively known as great filter theories. The idea here is that there's some obstacle, some filter that prevents civilizations from reaching the point where they can spread across the galaxy. The terrifying question is whether that filter is behind us or ahead of us. If the filter is behind us, perhaps it's the origin of life itself, or the development of complex cells or intelligence. That would mean we've already passed the hardest test, and our future is potentially bright. But if the filter is ahead of us, that's genuinely frightening. It would mean that something happens to virtually all technological civilizations before they can colonize their galaxy. Maybe civilizations inevitably destroy themselves with nuclear weapons, or bioengineered plagues, or artificial intelligence that gets out of control, or environmental collapse. Maybe there's some technology that seems beneficial, but is actually civilization ending, and every species discovers it and uses it without realizing the consequences until it's too late. On November 2nd, 2001, something strange happened in the data archives of the Parkes Radio Telescope in Australia. A burst of radio waves, lasting just a few milliseconds, had been recorded 6 years earlier in 1997. It was incredibly bright, incredibly brief, and came from somewhere far beyond our galaxy. The astronomer who discovered it, Duncan Lorimer, had no idea what he was looking at. Neither did anyone else. This was the first detection of what we now call a fast radio burst, or FRB, and it opened up one of the most intriguing mysteries in modern astronomy. Fast radio bursts are exactly what they sound like. Extremely brief flashes of radio emission that appear suddenly from random points in the sky and then vanish. We're talking about bursts that last anywhere from a fraction of a millisecond to a few milliseconds at most. But don't let their brevity fool you. These bursts are extraordinarily powerful. In those few milliseconds, a single FRB releases as much energy as the sun emits in several days, or in some cases, even years. And they're coming from billions of light years away, from distant galaxies far beyond the Milky Way. When the first FRB was discovered, many astronomers were skeptical. Was this really an astrophysical phenomenon, or could it be interference from Earth-based sources? Radio telescopes are incredibly sensitive instruments, and they pick up all sorts of signals: satellites, aircraft radar, even microwave ovens. There's a famous case where astronomers spent years investigating mysterious signals that turn out to be coming from the microwave in their break room, being opened before the timer finished. So when Lorimer announced this discovery, the scientific community wanted more evidence. That evidence came slowly at first. A second FRB was detected in 2012, then more trickled in. Each detection confirmed that these were real astronomical events. The signals showed a characteristic property called dispersion. Lower frequency radio waves arrived slightly later than higher frequency waves. This happens when radio waves travel through the plasma between galaxies, and the amount of dispersion told astronomers that these bursts were coming from cosmological distances billions of light years away. These weren't glitches or terrestrial interference. Something out in the distant universe was producing incredibly powerful radio flashes. By the late 2010s, new radio telescopes with wider fields of view, like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, started detecting FRBs regularly. We went from having a handful of detections to discovering dozens, then hundreds. As of today, we've detected thousands of these bursts. And with more data came more mysteries. The first major puzzle was what could possibly produce such energetic bursts in such a short time. The brevity of the bursts tells us something important about their source. It has to be small. An object can't flash on and off faster than the time it takes light to cross it. Since these bursts last just milliseconds, the source region must be no larger than about 1,000 kilometers across. That's roughly the size of a small asteroid or a planet like Earth. But how could something so small release as much energy as the sun produces in days or years? Astronomers proposed dozens of theories. Maybe they were caused by colliding neutron stars, the incredibly dense remnants of dead stars. Maybe they came from evaporating black holes in the final moments of their existence through Hawking radiation. Maybe they were produced by strange, exotic objects called magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. Or maybe, and this was the suggestion that captured public imagination, they were artificial signals from advanced alien civilizations. The alien hypothesis was always unlikely from a scientific standpoint, but it couldn't be completely dismissed without more evidence. After all, we were seeing powerful, brief radio signals from across the cosmos. If you were an advanced civilization wanting to broadcast your presence or communicate across galactic distances, powerful radio bursts might be one way to do it. But as we gathered more data, the artificial origin explanation became increasingly implausible. The bursts appeared random, showed no obvious patterns or information content, and came from too many different galaxies. Unless the universe was teeming with civilizations all broadcasting similar signals, which seemed unlikely, these had to be natural phenomena. The breakthrough came in 2020, and it came from our own galactic backyard. On April 28, 2020, multiple radio telescopes detected an extremely powerful FRB coming not from a distant galaxy, but from within the Milky Way. The source was a known magnetar called SGR 1935 plus 2154, located about 30,000 light-years away. This was the smoking gun astronomers have been waiting for. For the first time, we had definitively connected an FRB to a specific type of object. Magnetars are neutron stars, the collapsed cores of massive stars left behind after supernova explosions. A neutron star packs more mass than the sun into a sphere just 20 kilometers across. The density is so extreme that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. Magnetars are neutron stars with magnetic fields amplified to truly absurd levels, often more than 1 quadrillion times stronger than Earth's magnetic field. These are the strongest magnetic fields known to exist in the universe. The magnetar explanation makes sense for several reasons. The enormous magnetic fields can store tremendous amounts of energy, and instabilities in these fields can release that energy suddenly in violent eruptions. The compact size of a neutron star matches the brief duration of the bursts, and magnetars are known to produce other types of high-energy outbursts, like X-ray flares and gamma-ray emissions. The 2020 galactic FRB showed that at least some FRBs come from magnetars, probably most of them. But here's where the mystery deepens rather than resolves. While we now think magnetars are responsible for FRBs, we still don't understand the exact mechanism. How do magnetar magnetic fields produce these specific radio bursts? What triggers them? Why are some FRBs one-time events, while others repeat from the same source? Imagine two different groups of detectives investigating the same crime, using completely different but equally reliable methods, and coming up with contradictory conclusions about when a crime occurred. Both groups have solid evidence, impeccable credentials, and have checked their work repeatedly. Yet their answers don't match, and the discrepancy is too large to ignore. This is essentially what's happening in cosmology right now, and it's causing what some scientists are calling a genuine crisis in our understanding of the universe. Welcome to the Hubble Tension. The Hubble constant is one of the most important numbers in cosmology, named after Edwin Hubble, who discovered the universe's expansion. It tells us the current rate at which the universe is expanding. Specifically, it tells us how fast galaxies are receding from us for every megaparsec of distance between us and them. A megaparsec is about 3.26 million light years. So, the Hubble constant essentially describes how the fabric of space itself is stretching. You might think that measuring a single number would be straightforward, especially with all our modern technology and sophisticated instruments. But here's the problem. When we measure the Hubble constant using observations of the early universe, we get one answer. When we measure it using observations of the nearby, late universe, we get a different answer. And the gap between these two measurements has been growing more significant as both methods have become more precise. Let's start with the early universe measurement. The primary tool here is the cosmic microwave background, or CMB, the afterglow of the Big Bang. About 380,000 years after the Big Bang, the universe had cooled enough for neutral atoms to form, allowing light to travel freely through space for the first time. That light has been traveling through the expanding universe ever since, and we can detect it today as microwave radiation coming from all directions in the sky. The CMB is like a baby picture of the universe, showing us what conditions were like when the cosmos was just an infant. The CMB isn't perfectly uniform. It has tiny temperature fluctuations, variations of just a few millionths of a degree, but these fluctuations are incredibly important. They represent the seeds of all the structure we see in the universe today. Galaxies, galaxy clusters, the cosmic web. The pattern of these fluctuations is exquisitely sensitive to the fundamental parameters of the universe, including the Hubble constant. The Planck satellite, launched by the European Space Agency, measured the CMB with extraordinary precision. By analyzing the pattern of temperature fluctuations, along with our best theoretical model of the universe called lambda-CDM, which includes dark matter and dark energy, scientists calculated what the Hubble constant should be. Their answer, approximately 67 kilometers per second per megaparsec. This means that for every megaparsec of distance, galaxies are receding about 67 kilometers per second faster. This measurement is incredibly precise, with an uncertainty of less than 1%. Now, let's look at the late universe measurement. This method is more direct and uses what's called the cosmic distance ladder. It's a step-by-step approach to measuring distances to farther and farther objects in the universe. The process starts with nearby stars whose distances we can measure very accurately using parallax, the apparent shift in their position as Earth orbits the Sun. Then we use these nearby stars to calibrate the brightness of certain types of variable stars called Cepheids, which pulsate with a period that's directly related to their intrinsic luminosity. Cepheid variables are crucial because once we know the relationship between their pulsation period and intrinsic brightness, we can measure their periods in distant galaxies, calculate how bright they should be, compare that to how bright they appear, and thus determine how far away those galaxies are. Then we can use those galaxies to calibrate even more distant objects like type I supernovae, which can be seen across billions of light years. By measuring both the distances to these galaxies and their redshifts, which tells us how fast they're moving away, we can directly calculate the Hubble constant. The most precise measurements using this method come from a project called SH0ES, led by Nobel laureate Adam Rees. They've used the Hubble Space Telescope to observe Cepheids and supernovae with unprecedented accuracy. Their answer, approximately 73 kilometers per second per megaparsec. Do you see the problem? That's a difference of about 6 kilometers per second per megaparsec, roughly a 9% discrepancy. That might not sound like much, but in cosmology, where measurements have become incredibly precise, this is huge. And it's not going away. As both teams have refined their measurements and reduced their uncertainties, the gap has remained. In fact, the statistical significance of this discrepancy has only grown stronger. We're now at a point where the probability that this is just a statistical fluke or measurement error is vanishingly small, less than 1 in a million. So what's going on? There are several possibilities, and each one is profound in its own way. The most mundane explanation would be that there's some systematic error in one or both measurements that hasn't been identified yet. Maybe there's something wrong with how we're measuring distances using Cepheids, some effect we haven't accounted for. Or maybe our interpretation of the CMB is flawed in some subtle way. Both teams have looked exhaustively for such errors and haven't found them. But that doesn't mean they don't exist. Systematic errors can be insidious and difficult to spot. However, the fact that completely independent measurements using different methods for the late universe, such as measurements using gravitational lensing or water masers, also tend to give higher values in the CMB prediction, suggests that this isn't just an error in the Cepheid method. Something deeper might be going on. One of the most fundamental questions in physics is also one of the simplest. Why does anything exist at all? Not in a philosophical sense, but in a very literal, physical sense. According to our best understanding of particle physics, this universe shouldn't exist. Or rather, it should be a universe of pure energy with no matter whatsoever. The fact that you're reading this, that stars shine, that galaxies exist, that matter exists in any form, is a profound mystery that strikes at the very heart of the laws of physics. Here's the problem. In particle physics, almost every particle has an antimatter counterpart. For every electron, there's a positron with the same mass but opposite charge. For every proton, there's an antiproton. For every neutron, an antineutron. These antimatter particles aren't just theoretical constructs. We can create them in particle accelerators, and they behave exactly as predicted. When a particle meets its antimatter counterpart, they annihilate each other in a flash of pure energy, converting their mass entirely into photons according to Einstein's famous equation, E equals mc squared. Now, according to the fundamental symmetries of physics, particularly something called CPT symmetry, the laws of physics should treat matter and antimatter exactly the same way. When a universe began in the Big Bang, the intense energies should have created equal amounts of matter and antimatter. Particle-antiparticle pairs would have spontaneously formed from pure energy as the universe cooled. For every quark created, an antiquark. For every electron, a positron. Perfect symmetry, perfectly balanced. But here's what should have happened next. As the universe expanded and cooled, all that matter and antimatter should have found each other and annihilated. Every particle should have met its antiparticle, and they should have destroyed each other, converting back into photons. The end result should have been a universe filled with nothing but light, pure electromagnetic radiation expanding through empty space. No atoms, no molecules, no stars, no planets, no life. Nothing but photons flying through the void forever. Obviously, that's not what happened. We exist. The universe is filled with matter. Galaxies, stars, planets, you mean everything we can observe is made of matter, not antimatter. There's no evidence for significant amounts of antimatter anywhere in the observable universe. We don't see the characteristic gamma-ray signatures that would result from matter-antimatter annihilation at the boundaries between matter and antimatter regions. The universe is overwhelmingly, almost exclusively, made of matter. So, somewhere, somehow, the symmetry was broken. For every billion particle-antiparticle pairs that annihilated each other in the early universe, there must have been one extra matter particle that survived without an antimatter partner. That tiny imbalance, roughly 1 part in a billion, is everything. Those leftover particles are what make up all the matter in the universe today. Every atom in your body, every star in the sky, every galaxy in the cosmos, all of it comes from that slight excess of matter over antimatter in the first moments after the Big Bang. But why? What caused this asymmetry? This is the matter-antimatter asymmetry problem, and it's one of the deepest mysteries in physics. To solve this puzzle, physicists look to something called the Sakharov conditions, named after Soviet physicist Andrei Sakharov, who outlined them in 1967. Sakharov identified three necessary conditions for generating a matter-antimatter asymmetry in the early universe. First, there must be processes that violate baryon number conservation, meaning reactions that can create or destroy matter without creating or destroying equal amounts of antimatter. Second, there must be violation of what's called C-symmetry and CP symmetry, meaning the laws of physics must treat matter and antimatter slightly differently. Third, these processes must occur out of thermal equilibrium, meaning the early universe couldn't be in a perfectly balanced state when these processes occurred. We know that at least some of these conditions are met. CP violation, the difference in how nature treats matter versus antimatter, has been observed experimentally. In 1964, physicists discovered that certain particles called neutral kaons decay slightly differently than their antimatter counterparts. Since then, we've found CP violation in other systems as well, particularly in particles called beam mesons. The discovery of CP violation earned the 1980 Nobel Prize, and further work on the subject earned another Nobel Prize in 2008. But here's the frustrating part. The amount of CP violation we've observed in the standard model of particle physics is nowhere near enough to explain the matter-antimatter asymmetry we see in the universe. We're short by many orders of magnitude. The tiny CP violations we've measured in particle physics experiments could account for maybe 1 part in 10 billion, but we need to explain an asymmetry of about 1 part in a billion. The numbers don't add up. This means there must be additional sources of CP violation beyond what's in the standard model. Physics we haven't discovered yet. This is actually exciting from a physicist's perspective because it means the standard model, despite being incredibly successful at describing particle physics, is definitely incomplete. There's new physics out there waiting to be found. One popular candidate for explaining the asymmetry involves neutrinos, those ghostly particles that barely interact with anything. Neutrinos are peculiar in many ways, and they've already surprised us several times. We now know that neutrinos have mass, even though the original standard model predicted they should be massless. We also know that neutrinos oscillate, changing from one type to another as they travel, which was another surprise. Some theories propose that in the very early universe, there were heavy versions of neutrinos called sterile neutrinos that decayed asymmetrically, producing more matter than antimatter. This mechanism is called leptogenesis because it first creates an asymmetry in leptons, the family of particles that includes electrons and neutrinos, which then gets converted into a baryon asymmetry through certain quantum processes. Leptogenesis is attractive because it connects to other mysteries like why neutrinos have mass and whether there might be right-handed neutrinos that we haven't detected yet. In the 1970s, Stephen Hawking made a discovery that would haunt him in theoretical physics for the rest of his life. He found that black holes aren't completely black. Through a quantum mechanical process now called Hawking radiation, black holes slowly evaporate, emitting particles and losing mass over unimaginably long timescales. This was a profound discovery that connected quantum mechanics, general relativity, and thermodynamics in a beautiful way. But it also created what might be the deepest puzzle in theoretical physics, the black hole information paradox. To understand this paradox, we need to start with what black holes are. When a massive star runs out of fuel and collapses, if it's heavy enough, nothing can stop the collapse. The star's core compresses down to a point of infinite density called a singularity, surrounded by an event horizon, the boundary beyond which nothing, not even light, can escape. This is a black hole, and it represents the most extreme warping of space-time that general relativity allows. For a long time, physicists thought black holes were simple objects. There's even a theorem called the no-hair theorem, which states that black holes are completely characterized by just three properties: mass, electric charge, and angular momentum. Everything else, all the detailed information about what fell in, the specific atoms, their quantum states, the exact configuration of matter, all of that gets lost behind the event horizon. A black hole made from collapsed stars is indistinguishable from one made from compressed encyclopedia collections or old cars or anything else with the same total mass, charge, and spin. Then came Hawking's discovery. Using quantum field theory in curved space-time, Hawking showed that the intense gravitational field near a black hole's event horizon creates particle-antiparticle pairs from the vacuum. Normally, these pairs would annihilate each other immediately, but near the event horizon, something different happens. One particle can fall into the black hole while the other escapes into space. To a distant observer, it looks like the black hole is emitting radiation, and because this radiation carries away energy, the black hole slowly loses mass and shrinks. This is remarkable because it means black holes aren't eternal. Given enough time, trillions upon trillions of years for stellar mass black holes, they will completely evaporate, disappearing in a final burst of radiation. For supermassive black holes like the one at the center of our galaxy, we're talking timescales of 10 to the power of 100 years or more, incomprehensibly longer than the current age of the universe. But eventually, they'll all evaporate. Now here's where the paradox comes in. According to quantum mechanics, information cannot be destroyed. This is a fundamental principle, as fundamental as the conservation of energy. If you know the complete quantum state of a system at one time, the laws of quantum mechanics allow you to calculate its state at any other time, forward or backward. Information is preserved. You might scramble it, encrypt it, spread it out, but you can't destroy it. This is called unitarity, and it's absolutely central to how quantum mechanics works. But what happens to the information that falls into a black hole? Suppose you throw a book into a black hole. That book contains information, the specific arrangement of atoms, the words on the pages, the quantum states of every particle. According to general relativity, that information crosses the event horizon and is lost to the outside universe forever. Even worse, when the black hole eventually evaporates through Hawking radiation, that information seems to be gone permanently. The Hawking radiation, as Hawking originally calculated it, is completely thermal, meaning it's random, like the heat from a fire. It contains no information about what fell into the black hole. The book's information has been destroyed. This is the paradox. General relativity says the information is gone. Quantum mechanics says information cannot be destroyed. Both theories are extraordinarily well tested and successful, but they can't both be right about what happens at black holes. Something has to give. The implications of this paradox are staggering. If information really is destroyed in black holes, then quantum mechanics, our most precisely tested theory of the microscopic world, is wrong in a fundamental way. We need to completely revise our understanding of quantum theory. On the other hand, if information is preserved somehow, then our understanding of black holes and general relativity must be incomplete. Either way, one of the pillars of modern physics needs to be fundamentally reconsidered. Physicists have proposed numerous solutions over the decades, and the debate has been fierce. Hawking himself initially argued that information is indeed destroyed, that quantum mechanics needs modification in the presence of strong gravity. This was a radical position that most physicists found difficult to accept. Others proposed that information isn't destroyed, but remains encoded on the event horizon. This led to the development of the holographic principle, one of the most profound ideas in theoretical physics. The holographic principle suggests that all the information about the three-dimensional interior of a region of space can be encoded on its two-dimensional boundary, like a hologram. For a black hole, this means the information about everything that fell and is somehow encoded in the structure of the event horizon itself. When a black hole evaporates, this information gets released in subtle correlations in the Hawking radiation that we initially missed in our calculations. This holographic idea has been developed into something called the AD/CFT correspondence, a mathematical framework that relates theories of gravity in certain types of space-time to quantum theories without gravity in one fewer dimension. This correspondence strongly suggests that information is preserved, and it's been a major focus of theoretical physics for the past 25 years. Many physicists now believe this is pointing toward the correct resolution of the paradox. Another proposed solution involves what are called black hole firewalls. This idea suggests that the event horizon isn't the smooth, uneventful surface that general relativity predicts. Instead, there might be a violent, high-energy region right at the horizon that would incinerate anything trying to cross it. This firewall would arise from the quantum mechanical requirement that information be preserved. If firewalls exist, they would radically change our picture of what black holes are like, but they also introduce their own puzzles and contradictions.